Hello friends, so welcome to the 36th lecture of this course. So as you remember, in past couple of lectures I have discussed the steepest descent method, which is coming from the class of non-stationary method. Here we are going to look another type of non-stationary method, which is called Krylov subspace iterative methods. So before going to the methods, I will introduce you what we mean by Krylov subspace. So let me write the definition of Krylov subspace. So let A be a n by n matrix having real entries and B be a column vector having dimension n. Then the Krylov subspace which is denoted as KJAB is defined as it means the jet Krylov subspace of A and B is the linear span of the vectors B, A into B, A square into B, and in this way up to A raised to power j minus 1 into B. And you can observe that again this Krylov subspace is a subspace of Rn, because all these vectors are having n components. So, all these vectors are coming from the vector space Rn. Let us take an example of it. Let A equals to 2 1 1 2 and B equals to 1 and minus 1. Then if I calculate AB, it will be 2 1 1 2 multiplied with column vector 1 minus 1, and it comes out to be 1 and minus 1, which is equals to A square B equals to A cube B and so on. So, here Krylov subspaces, that is if I write K1AB, K1AB will be the linear span, or let me denote this linear span by L of 1 minus 1 transpose. Similarly, K2AB will be linear span of vector B and AB. So, this will be linear span of B and AB are the same vector here. So, 1 and minus 1 transpose. So, in this way we can define the Krylov subspace. Next I will define Krylov matrix. Again let A be n by n matrix having real entries and B is a column vector having n component. Then Krylov matrix of jth order of A and B is the matrix having first column as B, the second column will become AB, and in this way the jth column will become A raised to power j minus 1 into B. So, in this way if I am having if I want to define nth order, so this j equals to n, and in that case it will become a square matrix of order n. Next, what is the motivation of using Krylov subspace for solving the iterative system? So, let us consider, so I want to talk about motivation. So, consider the matrix A, which is a 3 by 3 matrix having entries 0 to 1, minus 1, 3, 1, and then minus 2, 2, 3. Now, the characteristic polynomial of A is Ca lambda, which is just determinant of A minus lambda I, and if I calculate it, it comes out to be a polynomial in lambda of degree 3, which is lambda cube minus 6 lambda square plus 11 lambda minus 6. Now, by the Cayley-Hamilton theorem, we have, so what Cayley-Hamilton theorem tells us, that every matrix satisfies its characteristic equation. So, it means I can write A cube minus 6 A square plus 11 A minus 6 I, where I is an identity matrix of order 3 by 3 in this case, equals to 0, which is a null matrix of size 3 by 3. Or I can write from here, if A is an invertible matrix, then A inverse equals to 1 by 6 A square minus 6 A plus 11 I. So, what I have done? I have multiplied this characteristic equation, means in terms of matrix, by A inverse, and I have written in this way. Let us say this is a polynomial of matrix A. Now, so from here I can say that the inverse of A can be expressed in terms of as a polynomial of matrix A. Now, if we have a system X equals to B, where A is an invertible matrix, then the solution of this system can be written as X equals to A inverse into B, which I can write in case of this matrix 1 by 6 A square minus 6 A plus 11 I into B, which is nothing just P of A into B. If I do it, what I will get? 1 by 6 a square into b minus 6 a b plus 11 b. If you see this particular vector, that is a square b minus 6 a b plus 11 b, it is a vector, column vector having 3 components. So, 3 by 1 vector. This is just linear span of a square b, a b and b, which is means this vector can be written as in the linear combination of a square b, a b and b, which is in this form, and this is nothing just Krylov subspace, which is K3 AB. So, hence the solution of the system Ax equals to b is a vector from the Krylov subspace K3 AB. So, that is the motivation of using Krylov subspace for solving iterative system. Now, what I want to mention here, if A is a large and sparse matrix, but it is non-singular, then Krylov subspace method is a very effective method for solving linear system. We will get the solution with less computational complexity as compared to any other iterative method, standard iterative methods like Jacobi and Gauss-Seidel or some direct method. So, this is the motivation of using Krylov subspace method. One more thing I want to write about this, that is a main result. So, we can summarize this main result as let X equals to B be a linear system where A belongs to R n by n and B is a vector from n tuple real vector space. We do not care whatever large n, then there exists a real polynomial p given as Pt equals to j equals to 0 to m minus 1 alpha j t j, where alpha 1, alpha 2, all these alpha 0, alpha 1 up to alpha m minus 1, all these are scalars, all these are real numbers basically, such that the solution of system X equals to B can be written as X equals to P A into B, and this can be written as j equals to 0 to m minus 1 alpha j a j b. Here this is the P A. Now, it is not necessary here that m equals to n, means the degree of the this polynomial P t will be a characteristic polynomial of the matrix A. One of such case is the use of minimal polynomial, because minimal polynomial of a matrix A is also 0, and from there we can find out A inverse, which is having fewer degree sometimes compared to the characteristic polynomial, and that is why I was saying that these methods are quite effective and having less computational complexity. Now, just try to formulate method using these subspacing. So, let me revisit Krylov subspaces. the Krylov subspace KJAB is the column space of the Krylov matrix, which is quite obvious because the columns of Krylov matrix is nothing just the vectors b a into b a square into b up to a raised to power j minus 1 into b. Now, for solving a linear system, we want to choose the best combination as our improved x j in jth iteration. If you are having x j minus 1. Now, there are various ways of defining this best, or there are various ways of choosing x j in jth Krylov subspace of A and B. So, let us see what are those ways. So, the first way is the residual R j, which is nothing just b minus a x j. So, choose x j in such a way from the Krylov subspaces k j a b such that the residual R j is orthogonal. So, R j should be an orthogonal vector to k j a b, means R j is orthogonal to all vectors from this Krylov subspace. If you use this strategy, then we will have a method that is called conjugate gradient method, or in short CG method. The second strategy is the residual R j has minimum norm for x j in k j b. So, if we follow this strategy, then the method name is, we got another Krylov subspace iterative method, that is called GMRES method. So, this is gradient method for minimum with minimum residual. The other way of defining this best may be R j, which is the residual, is orthogonal to a different space k j a t b. So, here you just notice that instead of A, I am having Krylov subspace of A transpose and B. This method is called biconjugate method. The next strategy is the error is a hedge minimum norm. So, the error in jet iteration has minimum norm, and this strategy we follow in a method called SIMLQ. So, in this way we are having these 4 Krylov subspaces method based on defining this best in different way. There are other methods also. In this course I will focus on this method, because if you know one method you can follow the other methods from the literature in a simple manner. So, let us learn what is conjugate gradient method. So, it is one of the standard Krylov subspaces method which is used when the system is large and sparse, but the matrix, that is the coefficient matrix A, is symmetric and positive definite, like in the case of steepest descent method. So, it is A is SPD in short. So, let us go to the algorithm, how this method executes. So, input is a symmetric and positive definite matrix A, which is the coefficient matrix of the linear system x equals to b, right hand side vector b, and an initial guess x 0, because it is a non stationary iterative method. So, we need some initial solution. In first step, compute R 0, which is b minus x 0, and it is same as in case of steepest descent. After computing this, set the search direction in the initial iteration as d 0 equals to r 0, which is again similar to steepest descent. Now, for k equals to 0, 1, 2 until convergence, do calculate alpha k, that is the step length, which is again same as in case of steepest descent. In initial iteration, then it will change, because later on we will make the change in the search direction. Then fourth step is compute x k plus 1 equals to x k plus alpha k d k, the same iterative equation as we are having in steepest descent. Next, from here this method will differ from steepest descent method. Compute R k plus 1 which was b minus x a into x k plus 1 in steepest descent, but here it will become r k minus alpha k d k. Then if r k plus 1 equals to 0, then stop, else calculate beta k which is r k plus 1 r k plus 1 upon r k inner product of r k plus 1 upon inner product of r k. Then what you do, compute d k plus 1 as means next search direction r k plus 1 plus beta k d k, and then end of your for loop. So, this is the complete algorithm for conjugate gradient method. If I need to explain this method theoretically, then let us have a quick look on it. So, let us have a quick look on the explanation of this method in theoretical sense. So, the conjugate gradient algorithm returns approximations, means in different iterations x j, that is the solution in jth iteration, as a vector of the sum of initial solution plus a vector from jth Krylov subspace of A and R 0, and this is true for j equals to 0, 1, 2 and so on, such that the error in jth iteration with a norm A should be minimum over a vector q which is from a polynomial of degree j minus 1 I minus a q a into x minus x naught, where the norm A is defined as square root x t a x for a given vector x. So, it is the norm induced by the matrix A. Now, if we look first step of this method means for going x 0 to x 1, what we are having x 1 equals to x 0 plus alpha 0 r 0. Now, this alpha 0 r 0 is a vector in K of 0 A of r 0. R 0 is alpha 0 r 0 is a vector in this Krylov subspaces, because this Krylov subspaces will be having vectors r 0 means scalar multiple of r 0. So, it is x 0 plus this one. Now, this belongs to x 0 plus k 0 k 1 sorry not 0. Here alpha 0 will become r 0 upon again if I write in this way d 0 t a d 0, and this is nothing just the square of the norm of r 0 upon square of the norm induced by the matrix A on the vector d 0, and it cannot be 0 because r 0 is not 0. Once r 0 is 0, method will not proceed. That is the termination or stopping condition for the conjugate gradient method. Now, residual r 1 will be r 0 minus alpha a 0 d 0. Again this will become a vector in the second Krylov subspace of A and B. Here if r 1 is 0, then method will stop, otherwise r 0 r 1 is an orthonormal basis of K 2 A B, which is the condition when I told you about 4 methods, that each time the residual r j will be a vector which is orthogonal to the jth Krylov subspace of A and r 0. So, in this way again when I will calculate r 2, then r 0, r 1 and r 2 will form an orthonormal basis for K 3 A B and so on. So, in this way we will proceed for subsequent iterations in conjugate gradient method. So, in this lecture we have learned the definition of Krylov subspace, then we have seen the motivation of using Krylov subspaces for solving large and sparse linear systems. In the last phase of this lecture we have learned the conjugate gradient algorithm. In the next lecture we will take an example of conjugate gradient method, and then we will see some conditions for the convergence of this method. Later on in the next lecture we will learn preconditioning of conjugate gradient method. These are the references for this lecture. Thank you very much.